So, good morning, all of you, and welcome to the next session for this energy analysis of closed systems that we are going to see in this course of thermodynamics and heat transfer. So, our discussion will start on energy analysis of closed systems, a fundamental concept in thermodynamics. This topic helps us to understand how energy is transferred and converted within a system. Closed systems are crucial in various engineering applications, which includes internal combustion engines, refrigeration systems, and power plants. So let's look into the closed system one by one, and we are going to see how the energy interaction occurs in a closed system. Coming on to the boundary work occurs when a system undergoes a volume change, causing it to perform work on its surrounding. A classical example is a gas expanding inside a piston cylinder device. As the gas expands, it pushes the piston outwards, performing work on the surrounding. Therefore, we can do this physical interaction between the system and the boundary with help of a mathematical representation. And this mathematical representation of this boundary work can be defined with help of the properties of the systems such as pressure, volume. Okay, so here the work which is obtained on this system is given by pressure multiplied by change in the volume. Now this pressure is exerted by the system on the surrounding, and the change in volume represents the volume which is the volume of the system which is going to change. Now with help of these equations, we can see that the work done is directly proportional to the pressure and the change in the volume. Now coming on to this boundary work calculations, the total boundary work is done over a process. So we have seen what is meant by process in the previous sessions, and this is given by the integral of pressure multiplied by change in volume, okay, over this process. It comes under the integral signs. Now this work is graphically represented as the area under the pressure volume diagram. The larger the area under the curve, the greater is the work done by the systems. So here we are using the application of the integration. You must have studied what is meant by integration in mathematics. Now this we are going to use for calculating the work, okay, the work done on a system. Okay, we are going to use the PV diagram in which the volume is on the x-axis and the pressure is on the y-axis, and this area under the PV diagram, okay, area under the curve will represent what is the work done on this system. Now you can see this is a PV diagram and the boundary work. As I told you early, in this what we are doing, we are using this y-axis for this pressure, x-axis for this volume. Now here the gas is going to expand from state 1 to state 2. The work done is shaded under the curve A. This curve A defines the process of expansion. Now this is a real world application of the piston cylinder arrangement, while the expansion of the gas results into a positive boundary work. So what is this positive boundary work? Means the work is not done on the system provides certain work output. Okay, so when we are compressing a gas, when the system is compressed, as we all know, the volume gets contracted, not expanded. Now, when this volume of the gas gets contracted, or we can say the volume, the final volume is less than the initial volume. Okay, for in that case, the pressure of the gas increases, and due to which the work should be done on this gas, and that work is a negative work. But the another case in which there is an expansion process, in which the volume of the gas increases, and consequently the final pressure is less than the initial pressure, then the system provides work. Okay, and this work is considered as a positive work. Now we will see the work done for different process path. As we have seen in the previous sessions, there are different processes such as isobaric process in which pressure remains constant, isothermal process in which temperature remains constant, isochoric process in which volume is constant, and the adiabatic process in which there is no heat transfer. So these are the different process paths in thermodynamics, or the special conditions in the thermodynamics. Okay. Now in this case, we see that a system can take a multiple paths. Okay, to transit from state 1 to state 2. Here we can consider the 3 paths. Okay, coming on to the path A. Now in this path, we can see there is a largest area under the curve, which results in the most work is done by the system. Okay, so here this is the work done is 10 kilojoules. Now in case of path B, okay, the area under the curve is less as compared to path A. So here we can see there is a less work of 8 kilojoules. In case of path C, we can see that here the area is very minimum under the curve as compared to path A and path B. Here, therefore, the work output is very less, that is 5 kilojoules. Now, from this, you can understand we are highlighting the key thermodynamic principle, which is that works depend on the process path, not just on the initial and final state of the system. Consider now the work done in a cycle. So what is a cycle? Cycle is a cyclic process in which the initial condition and the final condition is same. Okay, and this system returns to its original state after having the process. Now the net work done in the cycle is the difference between the expansion and the compression work. So we are seeing this. There is a cycle in which there is an expansion process and the compression process. These both processes are opposite, due to which after this process, the system gets to its initial states. After going through this process, the system gets to its original condition. Now in this case, if the cycle moves clockwise, okay, so it represents a power cycle, means there is a heat engine which is producing the net work. Now if this cycle is going into this counterclockwise direction, in which the compression process occurs first, then it represents a refrigeration or the heat pump cycle. And for this, we require the work input to the systems. Now the shaded area enclosed by the cycle represents the net work output. Now in this case, you can see that the concept which we are dealing with is the positive and negative work. Now in this refrigeration cycle, we have to do the work on the system. Okay, so when the work is done on the system, it is considered as a negative. But in case of a heat engine or any power cycle, when that system gives a certain work output, then it is considered as a positive work output. Now we will see an process which is called as a isochoric process. In this case, this isochoric process is a constant volume process. Constant volume means the initial volume and the final volume is same. Therefore, the change in volume in this case is 0. And the change in volume is represented by dV. So if dV is equal to 0, so what is going to happen for our work done? So work done is nothing but it is a product of pressure multiplied by change in volume. And if change in volume is 0, our work done is also 0. Now, if the work done is 0 and this is a constant volume process in which the other parameters such as pressure or temperature are going to change, so what change is going to happen in the systems? Now, if such is the case, now if there is no any work done, so there could be increase in the internal energy of the system. Now take the case in which the system properties are at state 1, the pressure P1 is 500 kilopascal and a temperature is T1, that is 150 degrees centigrade. And at pressure P2, the pressure is 400 kilopascal and temperature is 62 degree centigrade. So in this case, if we look into the matter, the final temperature is less as compared to initial temperature. Now, therefore, in this case, the heat is not in the system, the heat is not stored in the system, the heat is rejected from the systems because there is a fall in temperature of the systems. Now, if we use the second law of thermodynamics, okay, so from that we can determine the what is the net heat transfer. The net heat transfer can be obtained by calculating what is the net internal energy change of the systems. So here we can use the formula of mass of the air in the system multiplied by specific heat at a constant volume and multiplied by the change in the temperature. Now, if you carefully look at the formula, the mass is not a negative, the CV is also not a negative. The difference of final temperature and initial temperature would be a negative value because the final temperature is less as compared to initial temperatures. Therefore, the value of Q is negative. Okay, so when the value of Q is negative, it indicates the heat is transferred from the system. Okay, now in case of work, if the work is coming out from the system, we take it as a positive. But when the heat is coming out of the system, it is taken as a negative. Okay. Coming on to the next process, that is isobaric expansion process. As we all know, the term isobaric means pressure of the process is remaining constant or the pressure is constant. Now, in this case, we will analyze a piston cylinder system which is containing water. Now, the initial pressure of this system is 60 pounds per square inch. The mass is 10 pounds and the process is that we are going to add heat in the system at a constant pressures. Now, if the pressure is going to remain constant, now we can see that the volume is going to change. The initial volume of the system is 7.49 cubic foot per pound, and the final specific volume is 8.35 cubic foot per pound. So the work done by this process, we can be using our formula, pressure multiplied by change in volume. So P multiplied by V2 minus V1. Now in this case, if we see the value which we are getting, okay, that is a positive value. The pressure is a positive and V2 is greater than V1. Therefore, it will be a positive value. So when this WB, that is the work, boundary work, we get in a positive value, then we are going to see that certain work is done by the system. So when heat is added at a constant pressures, that results into both work done as well as increase in the internal energy of the systems. So how we can determine internal energy? We can use the formula mCp T2 minus T1. If we are adding the heat, then the final temperature will be always more than initial temperature. With help of this, we can determine what is the heat added into the systems, and according to it, with this formula, that is WB is equal to P multiplied by V2 minus V1, we will get what is the work done by the system. Now this next process is the isothermal compression of an ideal gas. Now from this isothermal word, we can understand that it is a constant temperature process. And in this case, there is a word which is known as, what is it is known as? It is a compression process. Now in case of this compression process, as we all know, we have to supply certain amount of work, okay, and due to which this is, we can say, work is done on the system, okay. Now if we want to find out what is the work which is done on the system, okay, now take us example in which the initial volume is 0.4 meter cube, final volume is 0.1 meter cube. The initial pressure P1 is equal to 100 kilopascal, and the temperature which is remaining constant, which is 80 degree centigrade. Now in this case, since the temperature is constant, and if we use the ideal gas law, what is ideal gas law? PV is equal to mRT. The mass is constant, R is also constant, that is characteristic gas constant, and the temperature T, which is also constant. Therefore, the product of pressure and volume becomes a constant value. And in this case, the formula for the work done gets modified, and it is given by W is equal to N multiplied by capital R multiplied by T, natural log of V1 by V2. Okay, here the N represents the number of moles of gas, R is the gas constant, and T is the temperature in the Kelvin. So with help of this formula, we can determine or identify what is the work of compression in the system. Let's see now the concluding remarks of these sessions. So we have started with the boundary work and the mathematical formula for this boundary work and its graphical representation using a PV diagram. You have seen work done in the different process path. Network, what is done in a cyclic process. Heat transfer in a constant volume and a constant pressure process. We have seen what is the work done in the isothermal compression of a gas. And these are the principles or the concepts which are very much essential for understanding the energy transfers in the engines, internal combustion engines, refrigeration systems, and power plant. So thank you. I hope you have understood these concepts. If any doubt or question, please feel free to ask me the questions or to drop me an email. Thank you.